Today we'll first discuss stopping time and strong Markov property. First, we give the definition of stopping time. So, stopping time is always associated with a specific stochastic process. So, let xn be a stochastic process. And the stopping time is a random variable defined on the index sets or the timeline. With values in the set plus. Basically here we restrict ourselves to the discrete time stochastic process. Okay, but it's not just any arbitrary random time. It has to satisfy some specific property. So here we go, such that for every value, the event is determined by the values of sequence of the stochastic process running up to that specific time point. So realize that the m here, and then this is basically saying if you're trying to determine the event t equal to m, then the necessary and sufficient condition would be looking at the stochastic process running up to a particular time. If you can do that in a necessary and sufficient way, then this particular random time is called a stopping time. So we have actually encountered the examples of stopping time before. So one of the example of that is the first passage time. In a simple random walk. Recall the definition of the first passage time. If you predefine a barrier C, then the first passage time Tc is defined as basically n xn equal to c. So now we can check the definition of stopping time to determine if t of c is the first passage time is a stopping time. So clearly, if you're trying to say Tc equal to m, it's sufficient to check the sequence, the realization of the simple random walk, its value up to x1 up to xm. It's a sufficient condition because if you can check the whole sequence, see the xm is the first time this random walk actually hit the barrier C here, And then it's absolutely necessary because you need all the sequence from x0 up to xm to see if that's the first time the random walk hit the barrier. So that's a simple example. The next example I'll give, that is a non-stopping time. So example 2 will be example of non-stopping time. Not every random time is a stopping time. So here, again, we use the example of simple random walk. So let's, in a simple random walk, let's define a random time. The last time the process hits certain barrier. For example, we start in the gambler's runes problem. The gambler starts with his fortunate 1, and then we ask the question, 1 is the last time it earns $2. So in this case, then, again, we go back to check the definition to examine, for example, a particular event, L equal to 100. Can this event uniquely determined by the value x1 up to x100? Clearly not, because we require the last time. The L is defined the last time. Given only the first 100 value is absolutely not sufficient to determine the event is true or false. We definitely need the values from x101, x102, and so on and so forth. So this is a violation of the definition. Therefore, the random time we defined, although it's a legit random time, it's not a stopping time. Okay, so hopefully now you're clear about the definition of stopping time. With the stopping time, we can start talking about strong Markov property. So the basic idea of strong Markov property is trying to generalize the Markovian property defined in the regular Markov chain and extend that idea to stopping time. So first, let's look at the precise definition, or the theorem 1 in the lecture notes. Again, the strong Markov property is always associated with a predefined Markov chain and stopping time. So let T be a stopping time for the Markov chain. Again, by default, just remind everybody, we're talking about the discrete time and discrete state space time homogeneous Markov chain. So if T is a stopping time for the Markov chain, then the strong Markov property says the Markov chain regenerate at time t. So this is basically saying the future which is defined by xt plus 1, xt plus 2 is conditionally independent of the past, which is defined by x0 up to xt minus 1. Obviously, this has to be given the value t and xt equal to x at the random time or the stopping time. So let's look at this definition. So it's the same, has the same flavor as the regular Markovian property, which we use to define the regular Markov chain. That is, given the present, the past, and the future become independent. However, there is a subtle difference, and then that difference is important, is the time here is random, and then it has to be a stopping time. If we write this into the mathematical formula, hopefully it will be clear that you will appreciate the difference between the strong Markov property and then just the regular Markov property. So this is basically saying, translate the theorem into a mathematical formula. That is the probability xt plus 1 equal to j given t equal to m and x0 equal to, let's say, I0 up to xm equal to I. So immediately this particular conditional probability is not the same as we have seen before, because this requires specific condition on the stopping time, the random times value. And the strong Markov property basically asserts this quantity is Pij, right? But the first thing you should notice is this is not the same statement as the regular Markov property, simply because you need to condition on more things. That additional thing is happen to be the specification of the stopping time, a random time. Okay, so how do we prove this? It's not actually that difficult, because by the definition of stopping time, you should realize the t equals m and the events because the t equals m is uniquely determined x0 up to xm. That means if I give you x0 up to xm, it contains the full information of t equal to m. So we can write this way simply. Again, the reason is the right-hand side contains the full information of the particular events t equal to m. That's by the definition of stopping time. So if this is true, then our equation is simply hold. So this is saying equal to m, sorry, 0 equal to I0 is no different than exam equal, which is Pij. So make it clear. Okay, so this is a basic idea proof. On the lecture notes, there's another version, but basically the same idea. Okay, so if you have a stopping time and then you have a Markov chain, well, what we have shown is simply saying the Markov property holds at a stopping time. And this is basically officially or precisely define what we mean by a Markov chain regenerates itself at the stopping time. So we have used that concept before when we talk about computing the first passage time or the first return time. If you're not familiar with that, go back to check your lecture notes on the random walks. All right, so how this whole thing related to today's lecture or the things we're gonna discuss in the future. So this is called implications of strong Markov property. Implications. Okay, so we can define a general first return time for Markov chain. So we define the first return time. So this notation denotes a Markov chain starting at state I and first return. To the same state. In n steps. Okay, so the probability of this event is defined as Fi n. So obviously this requires n greater than 0. And in general, we can define Fii equals n equal to 1 to infinity Fin. This simply represents the probability of the first return given x0 equal to I. Okay, so far we defined a quantity Fii that is basically the first return to a specific state I, that probability. And if we ever want to ask the question the probability of the Markov chain return twice or 3 times or 4 times or even more? How do you calculate? So what is the probability? MC return to state m times. Okay, the intuition is whenever the Markov chain returns, it regenerates itself, right? And so it becomes independent event. Given that the Markov chain already returned, the first return and the second return become independent. So how do you calculate the probability of return m times? That's a homework problem, but in that process, you will use the strong Markov property to argue what I just said. Given the Markov chain has returned to the original state, the first return, the second return, they are independent. The conditional independence is determined by this strong Markov property. That's a homework problem. The second topic we're discussing today is the communication class. The communication classes of a Markov chain concerns the connectivity of the states defined in the Markov chain. We say that a state J is accessible from state I if Pijn is greater than 0 for some So this is pretty simple. So if you look at the transition matrix and then particularly look at the n-step transition matrix and then figure out Pijn is greater than 0, that means starting from state I in n steps, there is a non-zero probability can reach state J, then we say state J is accessible from state I, and then we use this notation to denote J is accessible from I. And if it happens to be the case, I is accessible from J, and given the both things, we say I and J communicate with each other, and we use this double arrow to denote this communication relationship. So this is defined as communicate. So to determine the two states are communicated or not, is you can simply look at the transition probabilities or transition matrices if it's happened to be a finite state Markov chain. And all the information should be encoded in the transition probabilities. So immediately, we will notice the communication is equivalence relation. So this is a proposition 1 on the lecture notes saying communication is an equivalence relation. What does it mean? If you remember the algebra class, that means, first of all, a state is always communicates with itself. So this is called a reflexive. This is always true because of we have the convention equal to 1. So the second property of communication equivalence relationship requires symmetric relationship. That is, if I communicate with J, then it has to be the case J communicate with I. This is called symmetric. So this is basically by definition. So that we check the first two things. So the third requirement for an equivalence relation is for the transitive. That is, if I is communicate with J and J communicate with K, then I has to be communicate with K. So this is called transitive. Okay, so this needs a little bit of the proof, but it's actually simple because given the condition, the assumption I communicate with J, we say there exists M such that Pij M greater than 0. And the same thing, sorry, this is the wrong notation. It's exist. And then there also exists N here, such that Pjk N greater than 0. So now we're left to prove there exists there is some number of transitions that Pik is greater than 0. Actually, we can achieve it by M plus N. We're trying to prove this quantity is actually greater than 0. This is because we have shown last time by Chapman-Kolmogorov equation. This is simply integrating O to R, that's the all possible states after M transition, and then the N transition. So this is held by Chapman-Kolmogorov equation. Furthermore, we know for a particular R equal to K, those two probabilities are greater than 0. So it must be the case the whole thing is greater than or equal to P greater than 0. with this, we prove the pik m plus n is greater than 0. That shows I and k are communicate with each other. So all three properties have been shown to be true. The communication implies reflexive, symmetric, and transitive. That proves the communication is an equivalence relation. So what's the benefit of defining an equivalence relation? The immediate benefit of that is the communication induces a class. So if two states communicate with each other, then they are said to be in the same class. And furthermore, this is a concept. If the Markov chain contains only one communication class, the MC is said to be irreducible. So irreducible simply means there is only one communication class, and then every member, every state in this Markov chain communicate with each other. So that's the concept. So how do we do that to make a judgment in practice and to see if a Markov chain is to define its communication class? So from the definition, so what we have done so far is every piece of information come from the transition kernel, the transition probabilities. So in principle, we can examine the communication class by inspecting the transition probability. In example 1, so if we're given a finite state space Markov chain, it's 0.5, 0.5, 0, 0.5, 0.25, 0.25, and 0, a third, and 2/3. So if you're given such a transition matrix, the goal is to determine the communication class. So the very easy way to do that is translate this transition probability into a diagram. So clearly there are three states, just label 1, 2, and 3. Now we inspect each row. So there is a 0.5 probability. We start from state 1 and ends up in the state 1. So we draw an arrow like this. And there is another 0.5 probability transit from state 1 to 2. Now we done the first row, we move on to the second row. Starting from the state 2, there's a 0.5 probability going back to state 1, and then 0.25 to going back itself, and then the other 0.25 to go to state 3. we finish the second row, and then the third row is the same with a third probability. Go back to state 2, and 2/3 go back to itself. So now with this diagram, it becomes easy to check the communication clauses, right? So from 1, we can actually move from 1 to 2, that is here, and then 2 to 3. The same thing from 3, you can get to 2, and then to 1. So that means 1 and 3, sorry, are communicate with each other. The same thing, you find 1 and 2 are communicate with each other. 2 and 3 are communicate with each other. That means there is only one communication clause that includes 1, 2, and 3. And that's it. An important thing for the other kind of implication, the important implication from equivalence relation is we say a equivalence relation will induce a partition in the sample space. So this is a definition 2, or in the lecture notes. Or you should know this from the abstract algebra. So this is what just simply write induces of state space. That means every state in the state space S belongs to a communication clause and uniquely belongs to that. Every state in S belongs to a unique communication clause. And secondly, the communication clauses are mutually exclusive. And then the union of the whole class is S. So there's 3 properties. There's define the partition in a mathematical way, but this should be clear that every state belongs to one and only one communication clause, and then all classes are mutually exclusive. The joint of the all classes is the full space. Topic we're discussing today is recurrent and transient states. So before we formally define recurrent and transient states, we need a few notations. First of all, this notation Fij n, which is defined as the probability that a process starts at state I, and first keyword is first, enters state j at time n. So this probability actually related to the first passage time. If we define the first passage time from I to n, I to j, as a random variable, so this is a random time, that's the first passage time from I to j, we use this notation. Then I phi j, n is simply the probability, the first passage time from I to j equals n. Okay. A special case of the first passage time is the first return time. Now we consider IIN. So this concerns the first return time. That is the first time the process starts from I and returns to I. We just ignore the arrow back to I equals to n. Here, know the TI first return time for state I. And finally, we define the probability Fii as the summation in equal to 1 to infinity. So this quantity is basically accounts for the mutually exclusive events that this process back to I from time 1, 2, 3 back to infinity. So that's basically the finite return time. The first return time is finite given x0 equal to I. Alright, so we defined those important notations here. And we're going to use that repeatedly. Alright, with this notation, we can define the concept of the recurrent state. A state is a recurrent if Fii equal to 1. That means with probability 1, if the Markov chain starts at the state I, it will return back to the same state. If a state is transient, it simply means Fii is strictly less than 1. That means if this Markov chain starts at the state I, and there is a non-zero probability, it never returns. Okay, so to get familiar with these notations and then this definition. Based on this definition and notations, we can write out a relationship PIAN Fik, the first return time equal to k, that's the probability, multiplied by so in the homework, you are required to prove this equation. Just a little bit of the hint. The left-hand side is simply the probability xn equal to I. given x0 equal to I. And then the right hand side, you are doing the calculation by conditioning on more things. So that additional information you are conditional on is this. And to fully write out the right hand side, you would need a strong Markov property, which we discussed early today. Okay, this is the hint, and then you should get to the equation, this equation, and then that's critical for our proof of the property of a recurrent state. All right, intuitively, a state, if it's a recurrent or transient, so that property should be fully represented by the transition kernel or the transition probabilities of the Markov chain. So that's, we have the proposition 2. It's critically important. That tells you how to connect the recurrent or the transient status of a state by looking at the transition probability. So basically, this is saying the state I is recurrent if and only if okay, so the summation from n equal to 1 to infinity PIIN equals infinity. So this particular, the left-hand side of this equation has a particular interpretation. Again, I left that as an exercise. So if we can interpret the left-hand side, we'll discuss this in the next class. Okay, and to finish this proposition and this transient, if the condition is violated, okay, the key point of this proposition is, as I said before, is connect it's basically saying the recurrent and then the transient state, the status of a state is fully determined by the transition probabilities. So the question is, how do we prove this? The proof is not actually very difficult, but you do need to take advantage of the concept of convolution and utilizing a little bit of the generating function. Okay, so to start, we can define the generating function for the sequence PII and FIIN. First of them. So notice that this is not exactly the probability generating function, because none of these corresponding to a discrete random variable, but it's simply a random, it's a generating function for the sequence PIN here. So this is for the general generating function, we have the convergence radius, and we need to deal with the special case. We say this PI0 equal to 1. Okay, accordingly, we can define a generating function for Fii sequence. We can make it from 0 to infinity, Fin. Excuse me, this is a mistake. So the same radius and the boundary condition. So this makes sense. You're asking the first return of the 0 step. The first return must be 0. Okay, with this two definition, we're hoping to connect these two generating functions through the recursive, the relationship we just stated. And hopefully you have proved that in the homework. K, P, n minus k with the condition n. Because now look at this boundary condition pii at n equal to 0, this equation simply doesn't hold because we require Fii 0 equal to 0 and Pii 0 equal to 1. So the equation holds as long as n is greater or equal to 1. Utilizing this equation, we can connect this equation with the generating function by simply adding the polynomial s to the k on the right hand side. Okay, so if we further summarize everything from n equal to 1 to infinity, and then we can actually add an additional term for n equal to 0 on the right hand side, multiply by Pii 0 s to the 0. This term is simply 0 because Fii 0 is 0. But the right hand side, the whole thing is simply g of s, Gii multiplied by Fiis. Okay, but the left hand side here, you should realize that's Giis with a missing term. That's the term n equal to 0. So that's this term. So put everything together, we have this equation derived from the convolution. And this should help us to prove the proposition 2. We prove, first we rewrite this equation to the form now. First assume state I is recurrent. Then by definition, that would require summation of if I in 1 to infinity or 0 equals 1, which implies 1 over FIIS, taking a limit s goes to 1, what goes to infinity. So this only holds as the left-hand side of this term. Which just happen to be so that's proof one direction. So the other direction is even easier. So if we have assumed, so we have this condition assumed, sum over O the PIIN goes to infinity, then the FII, then it has to be the case. Otherwise, you can prove by contradiction. If this term is non-zero, then you have a finite, the 1 minus FIIS as s goes to 1 is a finite number. So that's a contradiction. So by contradiction, you can prove from the other direction. That's basically proves proposition 2. So I'll end today's lecture here, and then we continue our discussion on other properties of recurrent and transient states next week.